All right. Hello, everyone. My name is Youngchan, and today I'll talk about subset selection methods from Chapter 6.1 of ISLP. In this presentation, I'll first explain why model selection is necessary, then introduce three different subset selection methods, and finally, I'll apply those concepts to solve problem set 5. Okay, our contents are like this. Why do we need model selection? What is subset selection? Three types of subset selection, and problem A to C, connection to modern machine learning, and conclusion. First, why do we need model selection? When we build regression models, we often have many predictors that might explain our response variable y. If we use too many predictors, our model may fit the training data perfectly, but fail to generalize to new data. That's what we call overfitting. On the other hand, if we use too few predictors, our model becomes too simple and misses important patterns. That's underfitting. So, model selection is about finding the right balance between complexity and performance. In other words, we want a model that performs well not only on the data we trained on, but also on unseen test data. Let's see the graph. As you can see the sweet spot where bias and variance are balanced. It represents the optimal model complexity. Let's go to next slide. Right. What is subset selection? Now, let's understand what subset selection really means and how model flexibility affects performance. Subset selection is about choosing a subset of predictors that best explains the response variable y. Suppose we have p predictors, then we can build models with 0 predictor, 1 predictor, 2 predictors, and so on up to all p predictors. That gives us p plus 1 different models. For each of these models, we can compute the residual sum of squares. We call it RSS, which measures how well our model fits the data. In regression, we usually measure model error using the RSS. So in this talk, whenever I say error, I'm referring to the RSS value. Let's go on. Mistake. Here we have two important versions of RSS. First, training RSS, which measures how well our model fits the training data. Second, test RSS, which measures how well it performs on unseen data. As we add more predictors, the training RSS always decreases. It means that the model fits the training data better and better. But as we can see in this graph, let's see the graph. The test error behaves differently. It first decreases, reaches a minimum, and then increases again. This happens because when the model becomes too complex, it starts fitting the noise instead of the true underlying pattern. The best model, therefore, is not the one with the smallest training RSS, but the one whose test RSS is at its minimum. This is the key idea behind the model selection. We want the model that generalizes best, not just the one that memorizes the training data. Let's go to the next slide. Then let's talk about 3 types of subset selection. There are 3 common ways to perform subset selection. Those are best subset selection, forward stepwise selection, and backward stepwise selection. Let's briefly go through how each one works. Best subset selection fits all possible combinations of predictors. It's like checking every possible model and picking the one with the smallest training RSS. This method gives the global optimum, but it's computationally expensive because there are 2 of p possible models. Next, forward stepwise selection. It starts with no predictors. Then it adds one variable at a time, which improves its training RSS. It's much faster than best selection, but can't revise an early wrong choice. Backward stepwise selection is directly opposite from forward stepwise selection. It starts with all predictors included. Then it removes the least useful variable at each step. So far, we've seen how these 3 methods behave. Then now, let's actually apply them to the problem. The first question is, which of the 3 models with k predictors has the smallest training RSS? The answer is best subset selection. Why? Since best selection tries every possible combination of predictors, it always finds the combination that minimizes the training RSS for each case. By the way, forward and backward stepwise explore only limited paths, and it means that they might skip the best combination, so their training RSS can't be smaller than the best subset model. Let's go to the next problem. The second question is, which of the 3 models has the smallest test RSS? Interestingly, the answer is, it depends on each case. Even though best subset fits the training data perfectly, it might overfit and perform worse on new data. In practice, forward or backward stepwise selection sometimes achieve smaller test RSS because they are less flexible and therefore less likely to overfit. If we plot test RSS against model complexity, you'll see that it first decreases and then increases. So the best model is the one in the middle, not the most complex one. Finally, part C contains several true or false questions about how the models relate to each other. Let's go through them. Number 1. In forward stepwise selection, the predictors in the k-variable model are a subset of the predictors in the k plus 1 variable model. It's true. Very simple question. because we add one variable at each step. So K variable model must be a subset of K plus 1 variable model. Number 2, in backward stepwise selection, the predictors in the K variable model are also a subset of the K plus 1 variable model. It's true again, since we remove one variable at a time in reverse order. Let's go next slide. Number 3 and 4. Comparing forward and backward models directly. Unfortunately, it's false. They follow different paths, as we said before, so they're variables that aren't guaranteed to overlap. Finally, number 5. For best subset selection, the predictors in the K variable model aren't necessarily included in the K plus 1 variable model. It's totally false. Unlike stepwise selection, in best selection, each K is optimized independently. So there is no relationship between K variable model and K plus 1 variable model. Let's go to the next slide. Until now, we've learned 3 types of subset selection methods. There are best subset, forward and backward stepwise. These classical approaches are actually the foundation of modern machine learning models. For example, we're gonna talk about rich regression and lasso regression. Rich and lasso regression can be seen as continuous versions of subset selection. Instead of testing every possible combination of predictors like best subset does, they add a penalty term to the regression equation that automatically controls model complexity. In rich regression, we penalize the size of coefficients, making them smaller but never exactly zero. This reduces overfitting by shrinking the effect of less important predictors. And in lasso regression, we penalize the absolute value of coefficients. You can see equation in slide. As a result, some coefficients become exactly zero. It means that lasso actually performs variable selection automatically. It's similar to best subset selection, but it is much smoother and computationally efficient. So what we've learned here isn't just classical statistics. It's the conceptual origin of feature selection and regularization, which are now essential ideas in modern machine learning. All right, let's see the graph. In this graph, you can see how rich and lasso differ geometrically. Rich uses a circular constraint, as you see in the graph, which smoothly shrinks coefficients first, but it keeps all of them non-zero. Lasso, on the other hand, uses a diamond-shaped constraint. Because of its shape corners, the optimal solution often hits the axis, and it means some coefficients become exactly zero. This is why Lasso effectively performs variable selection, while Rich mainly reduces model variance. Okay, this is the final slide of our presentation. Let's summarize today's talk. Best subset finds the model with the smallest training RSS, but can easily overfit. Second, forward and backward stepwise are faster and often generalize better. Third, Reach and Lasso extend these ideas by automatically controlling model complexity through regularization. Finally, this is very important point. Always evaluate model based on test performance, not just training results. All of us should keep in mind this statement. All right. Subset selection reminds us of an important principle. The best model isn't always the most complex one. We should remember that the best model is the one that balances simplicity, accuracy, and interpretability. Okay, let's end this presentation. And thank you for listening.